Welcome to Algebra 2. Algebra 2 will start with Module 1, Analyzing Function. Analyzing function will cover domain, range, and behavior, attributes of function, parent function. Example question. How can you analyze function to solve real-world problems?
When I was a kid, I played all kinds of sports. Now, you're probably familiar with a lot of the events in track and field, but did you know they all use a ton of math? Let's take a look. In the high jump, it's the athlete who launches herself into the air. This is Anika. She is the national champion high jumper and is training for the Olympics. So, what kind of math goes into training for high jump?
You have to have your speed plus velocity plus your angle, and you have to get all those working with one another to create that force to the ground. So once you take off, I can get the gravel over the bar.
How far and how high she travels can be determined by her velocity at takeoff and that takeoff angle. It can be described by this equation. Math is everywhere in track and field. It can help pole vaulters choose the right pole. It helps them raise the height where they start their parabolic flight. In the shot put, the athlete's trying to throw a 12-pound metal ball as far as he can. The trajectory of the shot may look familiar. It can be explained by a quadratic equation. The distance it travels is determined by the angle it launches and how fast it's traveling. That's another reason math matters.
Domain and range. Students analyze key attributes of function, including domain, represented in interval notation, inequalities, and set notation. Range, represented in interval notation, inequality, set notation, and also determine end behaviors. Example question. How can you determine domain, range, and end behavior of a function? Study this video and take notes.
Is expressing the domain and range. I want to write it as an inequality. I want to use this thing called set notation, and I want to use this thing called interval notation. And then I want us to describe the behavior of the function at the end behavior. Lots of words here, and I want to introduce them to you with this first example. F of x equals x squared minus 2, which is a quadratic, which means its graph is a parabola, and I've graphed it right here. So, what does the domain and what does the range mean? The domain means the allowable x values. So the x values that we're allowed to input into the function to produce output values. So here, what's the function? The function will take an x and then square it and subtract 2. That's the output. So what are the allowable values? Well, you could take any x value at all and square it and then subtract 2. So in fact, the domain for this function are all the numbers on number line. And you can see this visually if you want. Just take a little line and ask yourself, will the graph eventually cross that point? Well, the graph only goes up to here, but you can extrapolate and see it keeps going up, up, up. It keeps moving further and further to the right. No matter where I pick, even some really, really far away number, you just have to go high enough on the graph and you will eventually see where that goes. So, in fact, the domain is going to be all real numbers for this function. So how do we write that? How do we say that you're allowed to put in any x value you want? Well, there's several ways of expressing that. So now I'm just going to show you some notation. This is just bookkeeping here. This is not math. This is bookkeeping. So there's the inequality way of writing the domain. So writing the domain, you can use it the inequality way, which basically says that I'm going to say, what are the allowable x's? Well, x can range basically as far left as you want, and you can go as far right as you want. And the way we denote that is by saying x can go from negative infinity up to positive infinity. These are just symbols. Remember, infinity is not a number. It's just a symbol that says boundless or endless. So this says you can go as far as you want into the negative world, and as far as you want in the positive world. You can go left or right, and all of that is allowed. This is an inequality way of writing the domain. Now, there's also a set notation way of writing the domain. This is just a different way of saying the exact same thing. This is a little bit more complicated, but it's not saying anything new. It's just language, it's just notation. And here it is. So, since, in fact, the domain is a collection of values, all the allowable values, we could write it as a set. A set is just a collection. So here's how you write a collection in math. You can use set notation by saying, this is the set, so we use a curly bracket to indicate set. It's the set of all x such that x lives between negative infinity and infinity. So it looks kind of the same thing, doesn't it, as the previous thing? But this is a fancier way of saying it, and here's how you read it. This is the set of all x such that x is greater than negative infinity and less than positive infinity. So this is just a way of reading it. The set of all x such that x lives in this particular range of values for x. Now, there's also then interval notation, which is a kind of a shorthand way of saying the exact same thing, where we don't even write the x. All we do is just give the outer limits and say we go from negative infinity to positive infinity. Now, when you look at this, there might be a little abuse of language if you remember that this is how you also write ordered pairs. But in the context of a domain, it's telling you the allowable x values. So the x values can range from negative infinity to positive infinity, and we use these rounded parentheses because we can't actually equal either of those because infinity is not a number. If you're allowed to equal one of the endpoints, then we use a square bracket, and we'll see that in the next examples. So, that's the domain. Now, what about the range? Well, the range turns out to be the corresponding idea with respect to the y values. What are the allowable y values that we're going to see? So what we want to do now is we want to ask ourselves, if we were to kind of cast a light on both sides of this function, and the light would create a shadow on the y-axis, what values would have a shadow? And where would the light go through? Well, you could see this actually with us taking a line and asking, does the graph cross the line? And check it out. See, in this region right in here, the graph never crosses the line. The graph's living way up here. It never gets that low. In fact, it starts at a y value of -2. Now, after -2, you see there's a point that will, at least one point, in fact 2 points, that will in fact hit that y value. So if you think about the shadow, you see that all the y values from -2 right on up to infinity are attainable. And so in fact, the range, which are the y values that we hit, are going to start from -2 and go out to infinity. So, if you want to write that as an inequality, no problem. Here's how you'd write it as an inequality. You would say that, we just say that y is greater than or equal to -2. Because it's saying that y is going to be at least -2 or greater. If you want to write it consistent with that, which might not be a bad idea, you can write it this way. You could say y is going to be greater than or equal to -2 and less than positive infinity. In fact, you know what? I think I like that better. So I am going to erase this thing. I like this way better because that's consistent. It looks kind of the same as the other way. Yeah, let's get rid of that. I don't like that at all. Okay, and so let's move this up and say we like this. And there we go. So you see, y is going to be at least -2, but then it can go as large as you want. Notice that I have, in fact, a less than or equal to here, but only a less than here because, again, infinity is not a number. So here's an example where you can actually see the inequality with an equal sign. Now, the other way we can write this is set notation. So set notation is the same thing as before, but now it's y values. So how would we write this? We'd say it's the set of all y such that y is going to be greater than or equal to -2, but always strictly less than positive infinity. Exact same way of writing that. And then if we use interval notation, same concept here. All I'm going to tell you are the values, and we know that it's a range, so we know that it's y, and we go from -2 to positive infinity. But here's the tricky part. I put this round parentheses because I can't be positive infinity, but notice that I'm allowed to equal negative 2, and so therefore I'm going to put a square bracket there. Phew! There's a lot of ways of writing the domain, a lot of ways of writing the range, but you see the idea. The idea is the domain, allowable x, the range, the permissible y's, and lots of different ways of writing them. What about that end behavior? That's just asking, as you go off, let's say to the right horizon, what does the function do? Well, as x gets bigger and bigger and bigger, goes to infinity, notice the y goes to infinity. As x gets smaller and smaller and smaller, the function goes to infinity as well. So we could write that as follows. We could say that as x approaches positive infinity, the function approaches positive infinity. However, as x approaches negative infinity, the function still approaches positive infinity. Both ends are going up. Smiley face parabola, as we're used to. Terrific. Let's look at another example and see even more of this new notation and the new language. So, here this is an exponential function, f of x equals 1/2 raised to the x power, and here's the graph. Very pretty subtle graph. So, first of all, what's the domain? So that's the first question I have on my griddle, is what's the domain? Name the domain. Well, let's take a look. That's the allowable x values. So if I take 1/2 and raise it to a power, is there any power that I'm not allowed to raise 1/2 to? Well, you can look at the graph and see the answer is no, because no matter what x value you pick, there will be a corresponding y value, and you can see that with this line. It always crosses the curve. Now, out here, it might not look like it's in a cross, but you can see that this thing continues and keeps getting higher and higher and higher, and is moving further and further to the left. So eventually, in fact, it will hit, somewhere further out the road. So in fact, here, again, just like before, we see that we can write this as an inequality, as saying x is strictly between negative infinity and infinity. We can use set notation, just like before, be the exact same answer. We'd read this as the set of all x such that x is in this particular interval. And then if we want to use interval notation, we would just say, again, we just look at those endpoints and we don't include them, and so we write like this. What about the range? Now this is going to be a little bit more interesting. So the range, well, those are the allowable y values. Now if you look at this picture, what do you see? Well, you see that it seems like the graph never gets down here. In fact, the graph keeps getting closer and closer and closer to the x-axis, but never actually touches the x-axis. Because notice that if you put in larger and larger values in for x, like 1 million, 1 billion, and so forth, 1/2 to that power is always positive, but getting smaller and smaller and smaller. It's approaching the x-axis, so it's approaching y equals 0. So what we see here is that this is actually what's called an asymptote. It never actually gets there, but in fact, anything below it doesn't happen, anything above it will happen. So if we put lights here and see where the shadow is on the y-axis, we would get everything on the y-axis above 0. Above 0, and that is going to be the range. So, in terms of an inequality, we could write it this way. We could say that y is greater than 0, less than positive infinity. No, I don't have less than or equal to, because it never actually becomes 0. It just keeps getting closer and closer and closer, but never actually equals 0. In terms of set notation, we could write the corresponding thing here, saying it's the set of all y such that y is within this range. It's greater than 0, but less than positive infinity. And then if you want interval notation, all you do is care about those kind of end values. But notice that we don't include either, and so I use those curved parentheses. And what about the end value? Well, the end value, as x gets bigger and bigger and bigger, what happens to the y? It's heading closer and closer to 0. So we see that, in fact, as x approaches infinity, the function actually is approaching 0. And what happens as x approaches negative infinity? You see what's happening to the y values? They seem to be getting bigger and bigger and bigger without bound. And so we'd say that by saying, as x approaches negative infinity, the function approaches positive infinity. Boy, I just threw at you a lot of notation and a lot of language. Take some time, take it all in. It's like learning any other new foreign language. It's going to take a while to make it real. But I thought if I just threw you right in the deep end at the beginning, we'll begin to be able to make some meaning and soon begin to splash and swim like an expert in no time. Here's wishing you happy trails in your swim through algebra, and I'll see you soon.